Welcome students, welcome to the next session of Strength of Metals 1. In the previous class, we have started our derivation, shear stress calculation at a section, right? So further we have given a basic introduction, like in pure bending theory we are going into considering a section which is having zero shear force and having constant bending moment. But in practical case, there is no section with complete zero shear force and complete constant bending moment. So it is varying from section to section. As the section is having a different shear forces, it will have different shear stresses, and those shear stresses will act along the transverse sections only. Due to the transverse sectional shear stresses, some complementary shear stress will act along the longitudinal layers. These points we have indicated. And for that calculation of shear stress at a section, we have taken an example, a simply supported beam which is having UDL over entire length, and on that length, why we have taken this example only? Because for the UDL of the simply supported beam having UDL will generate the shear force diagram and bending moment diagram, like from point to point the shear force value and the bending moment value are changing. So from point to point these two values are varying. So it is one of the example we can use for calculating variations. Okay. So point to point shear force is varying, section to section bending moment is also varying. So like that I am taking this example. In that portion we have considered is two sections, that is AB section and CD section, which are at a distance dx apart. Okay. So in that sections I am considering on the section AB shear force as F, M as bending moment. On the section CD, F plus DF as the shear force, M plus DM as the bending moment. And moment of inertia of the whole section, whatever is A, B, C, D, and as length of the beam is the same, so the moment of inertia will come from I is equal to BD cube by 12. So which we have indicated as BD cube by 12. And in that we should have to consider some things, and we should have to indicate the moment answers. As the simply supported beam with UDL is having completely sagging or positive bending moment, I am indicating that section. On the section left of AB, nothing but AB section line, I am indicating positive bending moment M. On the right side, nothing but on the DX length at the section CD, we are indicating the next moment, that is M plus DM. So these two are the bending moments we are indicating, and in that section we need to calculate shear stress at a point in the AB section. For that, I am considering a level EF which is being at a distance of y1 from the neutral axis. So for that, I have indicated neutral axis line. This neutral axis line is at a distance d by 2, and above the neutral axis we have indicated a level EF. The level EF on this section is at a distance y1 from the neutral axis. Okay, so this portion EF we can consider up to the DX length. Okay, that is up to the CD section, and we are considering the complete portion above the level EF in between the sections AB and CD. That when we indicate it, you can observe a simple rectangle with AB section indication, and that is being continued over DX length and indicating the neutral axis line. And when you want to indicate, you can indicate up to this. So this is the AB portion, that is the CD portion. There we have taken the level as EF, okay, and that portion up to the DX length. So this is the segment I am considering, completely in between the section AB and in between the section CD, and completely above the level EF in the DX length. And this portion is considered having infinite number of cylindrical elements. Each is having area as dA, and each element is having the length as dx. So this portion EF above the neutral axis or this neutral layer level, the complete portion is having so many number of cylindrical elements of length dx. So those cylindrical elements of length dx. In those elements, I am considering one such a cylindrical element, and for that cylindrical element, we are considering this is EF level, and above this EF level I have indicated a cylindrical element, and this is at a distance y from the neutral axis. Okay, so the cylindrical element I am considering, and on the cylindrical element I have to indicate what are the forces acting, what is the dimensions we are giving. That dimensions we have indicated as dx, length of the element, dA, cross-section area of the elemental cylinder, sigma is the bending stress acting on the section AB, sigma plus d sigma is the bending stress acting on the section CD, and also y is its distance from the neutral axis line, right? So for this elemental cylinder we have given all the components. So its area of cross-section is dA and its length is dx, and also it is at a distance y from the neutral axis line, and also it is having sigma stress at this position and sigma plus d sigma stress at this position. As stress we already know, we can indicate bending stress formula. So bending stress acting on the section AB is equal to, which is having m as a moment, so m by I into y, and on the section CD the corresponding stress indication is equal to sigma plus d sigma is equal to m plus dm by I into y. So these are the stresses acting on the element at a distance y from the neutral axis. So bending stress at a distance y from the neutral axis acting on the section AB. Similarly, bending stress acting on the section CD at a distance y from the neutral axis. And these two stresses are causing some forces by the multiplication into cross-sectional area. So the cylindrical element is having the cross-sectional area dA. Again, the same area is continued till the end, right? Here the stress different, area same. Along the dx length, again the same cross-section maintained, but stress was varying. So sigma plus d sigma into dA. These two are the forces acting at this level, forces acting at this level. These two forces are still acting on the same elemental cylinder or the single elemental cylinder. Okay, the two ends of the cylinder, the forces are different, acting along the same line but in the different directions, right? So when it is acting like this, the other one is acting like this. So the net or the unbalanced force, if anything excess is there, that unbalanced force will cause the body to move away. So when you see horizontal equilibrium, what happens when we are moving in this direction? The same quantity of force is coming in the opposite direction, the body will be in the horizontal equilibrium. But when I am pushing with some force, but the opposite value is more than that, what the body happens? It comes this way, right? So the pushing force from this direction is lesser than the coming force. The body will, that unbalanced, the remaining leftover force will cause the body to go back. So therefore that unbalanced force which is still acting on the element is difference of those two. That difference of those two we have got the unbalanced force as dm by I into y into dA, and the total unbalanced force acting. So what is this? This is the unbalanced force acting on the single cylinder. Only one elemental cylinder is there. On that elemental cylinder, from this direction I am applying sigma times dA as one side force, and on the other side it is having sigma plus d sigma times dA as the other force. So the net force or the unbalanced force still coming is d sigma times dA, that is equal to dm by I into y into dA. So the net unbalanced force which is causing or acting on the elemental cylinder. But such type of so many cylinders were there above the level EF we have said. Okay, so the total unbalanced force above the level EF in between the sections AB and CD can be calculated by considering all the sections in between the elements, in between the level above the level EF. So only one force on the cylinder we have set, and parallel to this, above this, so many cylinders we are observing, right? above the level EF, as EF is like this, so many cylinders like this were there. When we consider so many cylindrical actions, every cylinder will have some unbalanced force coming back. Okay, here from this direction I am applying some force, and the net force or the unbalanced force that is coming in the next section is remaining. Okay, the total unbalanced force above the level EF between the sections AB and CD can be calculated by considering all the sections. So individual elements. So force on this element plus force on this element. So force on 1, force on 2, force on 3. Like that. So many number of cylinders were there. Summing up all the unbalanced forces on these cylinders, what you can get? The total unbalanced force coming in this direction from CD to the AB above the level EF. So above the level EF, what is the unbalanced force coming will be calculated. So the total unbalanced force above the section or above the level EF, above the level EF is equal to summation of all. As we have already said, we will indicate summation, sigma summation or integration. So summation will be indicated when 1 plus 2 plus 3, like that. Individual items when we know, we can indicate. But here we are having a variable. That position is at a distance y. So for such type of indication, integrating individual forces and getting the total force above the level. Okay, above the level EF, individual force is on the element is like this, and the total force due to all the elements above the level EF is like this. So integration of dm by I into y into dA. dm and I are coming out as constant, integral y dA, and integral y dA I can indicate as y bar times A, and the left portion is dm by A. So y bar into A. So what is this y bar and what is this A, and what this is happening? So this is the only thing we have said. When I am pushing with one force on the section AB and some other force is acting on the section CD, the net force will cause the body to come in the opposite direction. Now I am considering at this level EF line is there, right? So on this level EF, some force above the level EF, some force is coming in this direction. So that is dm by I into A into y bar, the total force acting above the level EF. When you see the side view, so this is the portion and we have indicated all these things. So this is our cylindrical element, and okay, only. And what is that y bar and what is that A? Y bar is nothing but distance of center of gravity of the portion above the area, so for the area A, and capital A is area of the cross section above the level EF, that we can indicate as EFGH in the figure. See here I have indicated capital A and y bar. What is this capital A and y bar? That capital A, when you see like this, when you see the cross sectional view, you can observe EF level. Okay, above the EF level, some shaded portion is there. So that shaded portion's area is capital A. Above the level EF, the shaded portion's area is capital A, and that portion is having some center of gravity. Okay, so that area's center of gravity is there. From the center of gravity of the area to the neutral axis line, the distance is called as y bar. Distance of the center A and y bar will be like that. So this y bar and this A we have given. Due to this total unbalanced force acting above the level EF, the beam may fail due to the shear between the sections AB and CD. See here, this is the shear failure. It is length continued. This is the length of the beam that is continued. Okay, so maybe at some position we are having supports. So along the length we are having, and along the length over a dx length, this is happening. So the net unbalanced force is causing the body to split like this. This shearing, this failure, we call it as failure due to some shearing action. Remember, it's not like that. It is simply splitting and coming out. So it is coming in this parallel direction. the horizontal section of the beam. Okay, the horizontal section of the beam above the level EF offers some shearing resistance, right? As every particle is being interlinked or connected, what happens if any force is causing the body to move away, as they are getting attached, it will not allow the body to get dispatched or separated. So, the horizontal resistance will be offered at the level EF. This shear resistance must be equal to the total unbalanced force. Otherwise, how much resistance I am giving, that much resistance should be equal how much force I am getting. Okay. So, the total unbalanced force acting on this is equal to the total resistance offered by the body. Otherwise, the body will fail. I should have to show enough resistance. Otherwise, the force will cause me to go to fail. Okay. The shear resistance means the resistance I am offering, the resistance I am being, and the net force acting on me should be equal to the resistance I am offering, right? So, the resistance offered by the section should be equal to the shearing force acting on the section. Therefore, the shear resistance or the shear force at the level EF is equal to dm by I into y bar into A. Let tau be the shearing stress or the intensity of the horizontal shear which is at the level EF. Tau is the shear stress at the level EF. And area on which the tau is acting, on which area the tau is acting, see here. As we have already said, so this is our portion, right? So this is the width of the segment and this is the length of the segment. Okay, and we said there is some shearing happening. So the net shearing stress that is happening is along this plane, and shearing plane on which area the stress is passing, so that is B into dx. So on this area the shearing force will act, right? The shearing area, on which area the shear is applied, that is shear stress into area. So that value is tau into area, which is the area that is B dimension into dx, that is the shearing plane's area on which the force is acting, on which the body is having, right? So that portion's area I should have to indicate. So the shearing area is equal to B times dx and tau is the shearing stress applied. Now, small b is equal to width of the beam at the level EF. Yes, at the level EF, what is the width that I should have to indicate there? And shearing force due to the tau at the level EF is equal to tau times b. Tau times b times dx. Tau b into dx. Shear stress into on which the shear stress is acting, or the shearing area, shear area. Okay. And tau b dx. That is shearing force is equal to, shearing force offered by the section is equal to unbalanced force coming. So, shearing force is equal to unbalanced force, dm by I into y bar into dA. And that tau is equal to dm by dx, y bar A, 1 by I into B. As we have already given one more relation, the relation between shear force and bending moment, dm by dx is equal to F. So, that dm by dx I am replacing with capital F. So, tau is equal to F into A into y bar by I into B. So, F A y bar by I B. This one is the shear stress at the level EF. Shear stress acting at the level EF. Okay, the shear stress from the above equation is the horizontal shear stress at a distance y1. See here, you should have to remember this answer. This y bar is different and this one is different. So, at a distance y1 from the neutral axis, when we want to calculate, this is the answer. So, tau is equal to F A y bar by I into B. So, how we are substituting, how this equation is helping us. So, with a numerical, we will calculate. Okay, for that, I am taking a numerical problem. So, till now, we have completed the derivation of shear stress calculation at a section. For that, we have taken a simply supported beam being subjected to UDL. There we have considered two sections. In the sections, we have taken a level at that level which is y1 distance, and above the level there are so many number of elements will be there. In those elements we have taken one element and analyzed for the stress. Later we have calculated the force on the single element, and then we have taken summation of all the forces above that level, and that answer has given the total unbalanced force is equal to total shearing resistance offered by the section. So tau B dx is equal to total unbalanced force acting, and from that arrangement and using the condition the rate of change of bending moment is equal to shear force dm by dx is equal to F, we have got F answers replacement, and tau the shear stress at that level is equal to F A y bar by I into B. Now we are going into a numerical. A wooden beam 100 mm wide. Okay, a wooden beam is having 100 mm width and having 150 mm depth. Okay, so 100 mm width and 150 mm deep, and it is being simply supported over the span. Okay, when we see the cross section, that is appearing like this, and when I am seeing the side view, I can see only this length only. Okay, the length is 4 meters and it is having the depth of the section as 150 mm. And when we see the side view, that is the cross section. Okay, cross section of beam, and this is length of the beam. This one is depth. Okay, so this is the length and depth. When we see the cross sectional view, this is the appearance of the cross sectional beam with width also appearing. Okay, and on this, if the shear force at a section is 4500 newtons, so they are not indicating the loading value, they are not asking us to calculate anything, only they are indicating what is the shear force acting at some section. Okay, maybe at some section F is indicated as 4500 newtons. Okay, now find the shear stress at a distance 25 mm above the neutral axis. I should have to calculate the shear stress acting at a distance 25 mm above the neutral axis. So when we see this picture, as we have already said, it is a rectangular cross section. See here, 100 mm width, 150 mm depth. Simply a symmetrical or the symmetrical section. Symmetrical sections have rectangular, circular and squares, and also symmetrical eye sections. So this one is also another type of symmetrical section. So the neutral axis, where it will be located? It will be passing through the geometrical center. So half the depth. So firstly, I should have to indicate the neutral axis line. Okay, we have indicated the neutral axis line. Where it will be located? It will be located at half the depth of the beam. So that one is equal to 75 mm from top, 75 mm from bottom. Okay, so the neutral axis location we have given. In the neutral axis, at what position we should have to calculate? At a distance of 25 mm above the neutral axis. Okay, at a distance of 25 mm above the neutral axis, I should have to calculate the shear stress. Okay, so I need to calculate this answer. And we have given already for calculating the shear stress. Please remember the formula. What is the formula and what are the terms involved? So firstly, shear stress formula, tau is equal to F A y bar by I into B. So F A y bar by I into B. Individually, what are the individual terms we should have to think? Okay, tau is shear stress at the section. So at which section I am calculating, that is the shear stress at the top. And F is equal to shearing force acting on the transverse section. Shearing force acting on the transverse section. And capital A is, we are considering some section, and above that section, what is the area of the portion? That is A. Okay, I am considering a section. Above that section, what is the area of the portion? That is capital A. And y bar is, for this area, there will be a centroid. Okay, from that centroid or the center of gravity, there will be a distance. That one is y bar. Okay, so distance of center of gravity of this shaded portion from the neutral axis, that one is y bar. And capital I is moment of inertia of the whole section. Capital I is moment of inertia of the whole section, and B is width of the beam at the level I am calculating the shear stress. Width of the beam at the level I am calculating the shear stress. When you see the picture whole, you can see like this. We are having a beam 100 mm width, 150 mm depth, and we have indicated the nodal axis at the half the depth. So from the top that one is 75 and from the bottom it is 75. Again, from the nodal axis at a level of 25 mm, I should have to calculate the shear stress. So I have indicated this line. Okay, and from this Y1 is the location for the section. Okay, and above that level, I should have to indicate the remaining portion as shaded for our clarity. Okay, please remember generation of picture itself will give some clarity for you. Okay, so above the level, we should have to shade the area. Why that shaded area? Because that area is the capital A's answer. Capital A in the formula, that is this area value, this numerical area value. And in that area, we should have to indicate a center of gravity of the area, and that distance from the nodal axis is Y bar. Okay, now width of the beam, that one is 100 mm, and depth of the beam is 150 mm, and we are having the force as, how much they have given us the force? 4500 newtons. As the section is being symmetrical, the nodal axis is at half the depth of the section, just now we have said, and let tau be the shear stress acting at a distance 25 mm above the nodal axis. Yes, at the section about 25 mm above the nodal axis, I am considering tau as the shearing stress. Using the equation, tau is equal to F-A-Y bar by I into B. Please remember the formula F-A-Y bar by I into B, where capital F, the shear force, we have got as 4500 newtons, and capital A, individual I am calculating all the terms. Okay, so where capital A is equal to area of the beam above Y1. So we have got this section with 150 depth and nodal axis line, which is at 75 mm depth. In those, we have indicated our shear stress evaluating level, that one Y1 is equal to 25 mm, and above this portion we are having a shaded area, that one is capital A. Okay, capital A is area of the beam above Y1. So above Y1, what is the area left that we are calculating, and the remaining portion and the width. So 100 mm width into 50 is the depth. So 100 into 50, which we have got 5000 mm square, which is the shaded area as shown in the figure. So the area of the shaded portion is the area I need to consider. And then Y bar is distance of center of gravity of this shaded portion from the nodal axis. So how it can be calculated? For that, I should have to look at where is the center of gravity locates. So here, this measurement is 50 and this measurement is 25. Okay, so this half the distance, so 50 by 2 plus this is 50 by 2, and the remaining is addition of 25. So this one is 25. So 50 by 2 plus 25, which totally we have got as 50 mm is the center of gravity distance from the nodal axis of the shaded portion. And then the next calculation is I, moment of inertia of the section. As it is being the rectangular section, the formula is BDQ by 12. So which is 100 mm into 150 cube divided by 12. 100 into 150 cube divided by 12. We have got the moment of inertia of the section as 2812500 mm per 4. Okay. So this is the moment of inertia of the section we have got, and small b. What is small b in the formula? That is the actual width of the beam at the level we are calculating the shear stress. Okay. So the actual width of the section at a distance y1 where I am calculating the shear stress. As it is being the rectangle, every level the width of the beam is same only. That one is 100 mm. Maybe if it is a circular beam. Okay, this is my neutral axis. If this is the width, okay, and I need to write beam measurement as this value, not the diameter value. That's why I am indicating actual width of the beam at the level where we are calculating the shear stress, and this one is Y1 I am indicating. Okay, above this portion I need to consider. So this example we will do in the next condition. Okay, so this is actual width of the beam at the section at a distance Y1 from the above the neutral axis, that means 100 mm. And then substituting all these values in this shear stress equation, capital F is equal to 4500 newtons, and area we have got as 5000 mm square, and Y bar we have got as mm 50, and I is equal to 2812500 mm part 4. If you want, you can write the units as well. For getting the clarity later on, you don't need to write in the units. And B, the width of the beam is 100 mm. So, substituting all these values, I have got the shear stress at the level at a distance 25 from the neutral axis. Distance 25 from the neutral axis is 0.4 Newton per mm square. Okay, so in this way we are calculating shear stress at the section for the rectangulars, like symmetrical things, where at any section the width is same. If we go into some other section like a triangular section when we use as a beam, or a circular section, from section to section the width is varying. So such type of sections, using the different widths, we will calculate the shear stress in the next class. Thank you.